Rather than having a program for every possible permutation of an input, a convolutional neural network allows programmers to filter and categorize large sets of data by passing information through these convolutional layers that, like neurons, process the data relevant only to its receptive field. In deep learning, this information is then pooled into related categories and given different weighted values to solve the problem. The power of deep learning systems is evidenced by the fact that today's best checkers, chess, Go, Atari 2600, and even Jeopardy players are all computers running variations of these self-referencing CNN algorithms. The success of machine learning has also highlighted potential shortcomings in trying to understand the human brain through the surrogacy of computers. The first and most pronounced shortcoming is the amount of data these systems require to make reasonable answers to the problems that they are confronted with. In the case of IBM's Watson system that defeated the world's reigning human Jeopardy champion Ken Jennings, a vast database of 15 terabytes of general human knowledge was required. This is a lot of bytes of information. This is way more than humans have on hand when they are trying to solve problems, and it's particularly significant when considering the learning and problem-solving abilities of children. Essentially, what I'm presenting here is Noam Chomsky's poverty of stimulus argument. Computational approaches to learning fail to approximate human learning and understanding by this same poverty of stimulus reasoning. The problem is even more than simple exposure. Even successful algorithms, like the ones that learned how to play Atari video games on their own, are clearly not performing a learning function that is akin to what humans do. First, the program itself uses raw pixels as input data and derives its output from a value function that estimates future rewards. Humans, on the other hand, perceive the input of the video game holistically. Clusters and configurations of pixels are viewed as whole objects, like tanks or walls. These produce very different learning behaviors, whereas humans will make large movements that become, through repetition, more inhibited and more exact. The computer program initially makes small moves. And even after 100 trials, it may still appear that the computer has little real understanding about what it's doing. Humans generally understand the main objective of a game, like Breakout, after only a few trials. These differences suggest two very different types of learning. One that is through a memory-intensive system of comparisons, and one that is done through creative understanding and experience.